Hi, everyone. Welcome to the beginning of section 3 of our Introduction to Statistics for Astronomers and Physicists lecture course. This week, we're going to be starting with our discussion on Bayesian statistics. And as you're all aware, this lecture is going to be pre-recorded and then made available to you to watch in the week leading up to our lecture on the 9th of June. So please make sure you watch this lecture in its entirety before then. And then during our regular lecture slot, we're going to be holding a discussion session. That discussion session will cover any of the aspects of this particular lecture that you find interesting or that you want to know more about. So with that in mind, please make sure that you click onto the Slido, which you can see the QR code at the bottom corner of the screen here, and you can register your questions again as normal, anonymously, just like in the normal lecture on the Slido. But now you can do it in advance. That means that at our discussion session, we'll have a whole bunch of questions anonymously asked or otherwise that we can discuss. And all of you, obviously, you're also welcome to ask questions live if you have any. So we're going to start our lecture course on Bayesian statistics with a couple of sort of interactive exercises that I think are going to be very useful for you guys to understand how we go about doing Bayesian statistics and what Bayesian statistics is all about. So before we begin, I want you all to take a piece of paper and a pen and write down the answers that you have to the following sort of scenarios that we're going to go through. This will all be clear when you have as we go through it. So pause the video now, go and grab a pen and paper if you don't already have one. And please do this because it really is going to be very useful for you as we go through today's lecture and help you understand some things. And as I say here, it's also going to be it's only for you. All of these responses are totally personal. They have no bearing on what anyone else does, and you'll see why. And I think they're going to be very, very useful to aid your understanding. And also you might learn something fun along the way, just about how your brain works in a way that you didn't understand, or didn't think about beforehand. So please do pause the video now, go and grab your pen and paper. And when you have your pen and paper, we'll get cracking. So the scenario that we're going to be going through over the course of the first little part of this lecture is this one. It's the first night back at the pub after a long lockdown, which is all something that I'm sure we can identify with. And you meet at the pub with your friends, for a Coke or a beer or whatever, and you sit down and you all start discussing the various things that you did throughout the course of your pandemic, throughout the course of your lockdown at your house over the previous year or so. And as you're going through and discussing these things, three friends talk about things that they've done. And so scenario one is about one particular friend. And this friend announces to the group that he spent the lockdown teaching himself how to predict the future. And he says that not only can he predict everyone's individual futures, but he can also see in advance the outcomes of individual events. Now, obviously, this is quite a bold claim. And the group says to him, well, you're going to have to prove this, right? And you're going to have to prove yourself. And the way in which we want you to prove yourself is by correctly guessing the outcome of a fair coin toss 10 times in a row. Okay? Scenario number two is a second friend says that he spent the lockdown learning how to be a wine critic. Now, it's entirely possible that this friend has spent the last year going through all the finer details of learning how to become a sommelier, but it's also quite possible that that is a euphemism for spending the last year just drinking cheap wine out of a carton. Again, the group thinks that's a pretty bold claim, and they challenge this person to prove their skills. And the way in which they challenge that person to prove their skills is by correctly identifying whether an unlabeled glass of wine comes from a vineyard in France or a vineyard in Spain 10 times in a row. And the last scenario that we find ourselves in is a third friend says that she has spent the lockdown relearning how to play classical piano. She says that she learned to play the classical piano as a child, but had dropped out of it. And the long time in lockdown gave her an opportunity to relearn how to play the piano. The group, again, would like to challenge her to prove that she can actually play classical piano, but unfortunately, since there's no piano in the pub, they have to find another way of testing this particular skill. And so the way in which they decide is that they're going to test her knowledge by challenging her to correctly identify a classical music piece that was composed by either Beethoven or Mozart 10 times in a row. So these are the three scenarios that we have at the pub. And what we're going to do now is we're going to go through and talk about these different scenarios and what you think about how they're going to play out. So each of these scenarios presents us with a person who has a challenge that they have to win. Okay? Let's not, for the moment, think about it statistically. Let's think about this purely in terms of your gut instinct, right? What you think the person is going or is not going to do over the course of this challenge. And the way in which I want to do this is I want you to start by taking your piece of paper and pen and drawing 3 empty sets of axes. Okay, just like this one that I've drawn here, which has, a y and an x-axis, and on the x-axis we've labeled it as fractional chance of success. And we've done this 3 times. And so each axis is labeled scenario 1, 2, or 3. Okay, pause the video now. Once you've got those axes lined up, then click again, click start again. Okay, so what we're going to do is we're going to start by asking ourselves, what probability or what chance do you think each person in these 3 scenarios has of succeeding at their challenge, bearing in mind that the challenges all state that they have to correctly guess all 10 outcomes. Okay, this isn't a question of whether or not they'll get 1 right or 3 right or 7 right. It's a simple binary choice of they get all 10 or they don't get all 10. Okay, so given that information, I want you to come up with a single value of what you think the probability is that your drunk friend is going to correctly identify 10 coin tosses in a row. The wine critic is going to correctly identify 10 unmarked glasses of wine in a row. And that the classical musician is going to correctly identify 10 classical composers in a row. Now, there's a bunch of different ways that this could go, right? You could say that, okay, I think it's going to be 1%, meaning that there's basically no chance that the person is going to succeed in their challenge. And that would look something like this, where I've put a dotted line down here at 1%. You could say that it's 50%, meaning that you don't really know. It could go either way. They could succeed, they could fail, okay? And so in that case, your dotted line or your point or whatever would sit at 50%. 50% chance of success for that individual. Or it could be 99%. You could think to yourself that, well, I mean, that's basically a certainty that this person is going to succeed at their challenge, and therefore I'm going to mark the axis here at 100%. A fractional chance of basically 1. But we can go beyond just having this single point estimate. So we've got our point estimates now, and if you haven't got your point estimate, then again, pause the video, make your decisions, and then rejoin us. But now that we've got our point estimates, we can move forward and actually create a full probability distribution. So we can keep our point estimates where they are, and we can ask ourselves, how confident are we in our guess? How confident are we in what we've just put down with our dotted line? So if, for example, you're very confident that there's a 50% chance of them getting it right, then that very confident response would look like a narrow, say, Gaussian distribution centered on 50%. Okay? If, for example, you're totally unsure and you think that there's basically no way of knowing, it could go either way, all values are equally likely, all probabilities of success are equally likely, and therefore I have no idea, then that would be a uniform distribution. It would be centered on 50%, as we said, but it would be basically totally uninformative. It would be totally flat probability that says, I think that it's equally likely this person will fail as it is equally likely that this person will succeed, because I have absolutely no idea about whether or not this is going to be something that they can do. If you've picked very confidently one way or the other, like you think it's almost a certainty that this person will fail, or it's almost a certainty that this person will succeed, then you really need to ask, how likely is it that, or how rapidly does the tail of this probability distribution taper off? Is it, for example, are you very, very confident that they're going to fail, for example, in which case it would be this 0% probability in my dashed line with a very sharply dropping off tail. Or conversely, you could say, look, I think they're probably going to do it, but it's not beyond the realm of possibility that they could also fail. So there is some finite probability down here at 0, as well as some probability up here at 1. So go ahead now, take some time, think about what you think for each of these scenarios, go back to the scenarios, have a read through them, and come up with your PDFs, come up with your probability distributions for each of these scenarios. It's very important that you have these scenarios drawn before you continue. So if you haven't got them drawn, stop the video now and do it, and then restart once those distributions are drawn. Okay, so going ahead now, assuming that you've all got these graphs drawn and you've all got your ideas or your beliefs ready and put aside on this piece of paper. The time has come now for the challenges. The time has come now, we're actually going to do these tests, do these challenges, and see what the actual outcomes are for all of these different challenges. So the first scenario, the first person up is our drunken fortune teller, our friend who thinks that he can predict the future, or tells you that he can predict the future. And his challenge is to correctly guess a coin toss 10 times in a row. Now, we take a coin from our own pocket, so we know that it's a fair coin, and we toss the coin 10 times in a row. And he calls head or tail when the coin is in the air, and when it comes down, we look at the response. After 10 trials, it turns out that he guesses correctly every single time. Okay, scenario number 2. Our wine critic, our wine expert, we ask, in order to perform this test, we ask the barman to put together 10 glasses of wine that come from either France or Spain. He numbers those glasses 1 through 10 and gives them to us. Now, not even we know what the correct answer is here. We just know that there are numbers 1 through 10, and that's all. So this is very much a double-blind study. This is as good as, you know, human empirical studies can get. And we take these glasses to our wine tasting friend, and we give them to him, and one at a time, he tastes the wine, smells it, whatever, and he writes down on a piece of paper, 1, France, 2, Spain, etc., all the way through till number 10. After he's finished, we take this piece of paper back to the bartender, and we hand him the piece of paper, and he tells us that our wine tasting friend has correctly identified every single glass of wine. Okay? The final scenario is the classical pianist. Now, we wanted to make this a little bit of a challenge. And so what we do is we go through everyone's, phones, music playlists at the table, and we pick out 10 songs that are written by either Mozart or Beethoven. And we intentionally make this difficult by not picking the really, really popular ones, like the da, 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 right? We pick the ones that are quite difficult. We play 10 songs for our friend, and she correctly identifies all of the composers in each of the 10 outcomes. So this is the data. This is the outcomes of our trials, of our experiments. The question is, what do you think now? How has the observations of this data changed your opinion about whether or not they were telling the truth or they were lying? And so that's what we're going to do next. Now what we're going to do is I want you to draw up the same 3 probability axes that we had before again. So I want you to keep the ones that you've already got. Very important that you keep the ones that you've already got, but draw an additional 3 axes and leave them unlabeled. Once you've done that, so pause the video, draw up those axes. Once you've done that, join us back again. So what we're interested in knowing is how the observations of the data have updated what you think about the probabilities of telling the truth or lying, basically. How does the outcomes of the challenge change your opinions? So what we want you to do now is I want you to label each of your 3 panels like we had, scenarios 1, 2, 3. And this time the x-axis is going to say fractional chance that they're telling the truth, something to that effect. And in this axis, 0 means that they're lying, which means that they can't see the future, tell the difference between the wines, or tell the difference between the classical pieces. And 1 means that they're telling the truth, that they can see the future, that they can tell the difference between the wines, and that they can tell the difference between the classical pieces. So this is what your new axis should look like, something like this. And what I want you to do now is I want you to draw an updated set of curves, similar to what you had from the last curves, but now updated to reflect what you think, having seen the data. So given that your fortune teller friend has correctly identified 10 coin tosses in a row, which we know from what we've looked at before is a very, very difficult thing to do. What do you think? Do you think that maybe he actually has learned how to look into the future? Same sort of question for the wine taster. Now seeing the data, perhaps he did actually, put in a lot of effort over the lockdown and not just spend all this time drinking wine. Or maybe it was luck. What do you think? Once you've put these graphs together, so pause the video now, think about these responses and draw these graphs for yourselves. Now, again, these are just for you, so you don't have to worry about what you draw. It's nothing, you're not going to be showing these to anybody. It's purely for your own education. So think about it, put it down honestly, put it down, actually think about it for a bit and keep them nearby because we're going to be using them quite a bit during the course, or we're going to use them, during the course of this lecture. Okay, so that brings us to the beginning of today's lecture, to the beginning of our lecture about statistical inference with Bayesian statistics. What we're going to be talking about for the course of the next few lectures is something called Bayes' theorem and what Bayes' theorem means for statistics and what it means for statistical inference. I think that it's not unreasonable to say that the applications of Bayesian statistics in modern astronomy and modern physics are very, very widespread, and that you will use Bayesian statistics in one form or another, subconsciously or consciously, in essentially every day of your life. And we'll see why that is in a minute. What we're going to do today is we're going to go through the basics of Bayesian statistics. We're going to learn about Bayesian statistics, what it is, and how we use Bayesian statistics. And we're going to discover some of the really important parts of Bayesian stats. And then over the course of the next couple of lectures, we're going to delve into it a little bit more in terms of its application. So to start, we're going to draw a distinction between classical inference and Bayesian inference, classical statistics and Bayesian statistics. Now, we've not used the term classical statistics and classical inference so far, but when I start going through this, what you'll realize is that this is actually what we've essentially been talking about all along so far in this course, is classical inference. What we've been discussing primarily during the course of this lecture is trying to extract some information about a population omega from some sample of observations from that population. That process of trying to draw conclusions about a population from a sample is known as statistical inference. It's the whole purpose of this lecture course. And up until this point, we've been focusing on this thing called classical inference. So let's take an example. The example is that a forestry commission, you know, a group that looks over and protects forests, wants to know, or rather wants to estimate, the number of trees, or rather how many trees in a particular forest, a large forest, suffer from a particular disease. Now, it's impractical for them to check every single tree in the forest, right? That would take forever and wouldn't be a practical use of their time. So instead, what they're going to do is they select a sample of N trees and they test those N trees. We're going to define now the variable theta as being the true fraction of trees that have the disease in this forest. Okay? There are N trees in the sample, and if all trees are independent of one another, which let's say that they are, then the probability that any one tree has the disease is just theta, right? Because that's the true fraction of trees that have the disease. When we first formulated probability, it was a fractional occurrence. And so the probability of any tree being diseased is just theta. What we're going to define now is X, this thing here, to be the random variable corresponding to the number of diseased trees that we find in our sample of N trees. Okay? And what the commission is going to do is they're going to take this sample, or rather the number of trees that are diseased within this sample, the fractional representation of the disease within the sample of trees, and use that to draw some inference about the true value of the population parameter that we are interested in, theta, the underlying true probability of a tree having a disease, or rather the underlying true number of trees that have this disease given the entire number of trees in the forest. Now that inference can happen in a whole bunch of different ways. So it could be, for example, a point estimate, right? Where we say, oh, my theta has broken, where we say that the value of theta is, our estimate of the value of theta is 0.1. Okay, that might be our inference. We just take the arithmetic mean, or rather we just take the value, the number of diseased trees divided by N, and we say that is our point estimate for theta, and that value is 0.1. That's one way of doing this inference. Another option is we could look at a confidence interval, right? We could say that I think, or rather the data tells me that the value of theta lies between the values 0.08 and 0.12 at some confidence, some 95%, for example, confidence. So that is to say that there is a 95% chance that the true value of theta lies between the range 8% to 12%. We could look at a hypothesis test, which is to say that we have two hypotheses. One is that the true value of theta is less than 7%, and we might reject that hypothesis at some confidence, at some significance level, which would be an important thing to know, right? Because if the forestry is just interested in whether or not the disease is going to run wild, and the critical value for whether it runs wild or not is that 7% of the population or more has to have the disease before it runs wild, then this hypothesis test is really the thing that we're interested in. And so for that reason, you might use the hypothesis test as your statistical inference. You could use the data to derive a prediction. You could derive a prediction that says that given the number of trees in my sample that have the disease and what I know about how the disease spreads, I predict that a total of 15% of the trees will be infected by this disease in the next year, for example. Again, something that the Forestry Commission might be more interested in rather than knowing just the true fraction of diseased trees right now. And the last one is that you could just use it to define a decision, which is, not just a nebulous, a more nebulous thing, but rather a more finite thing of saying, I don't really care what exactly the value of theta is, but I'm going to take the estimate that I have of theta and use that estimate to make a decision that, all right, this is higher than I am comfortable with. We're going to systematically go through and rip out every tree that's diseased in the forest. Okay? Generally speaking, all of these inferences are made by specifying some model of probability, which is this conditional probability, the probability of X given theta. The conditional probability of X given theta, that is the probability of the observations given some model of the data. We're basically asking the probability, or rather the distribution of X given a single particular value of theta. Okay? This here is what we call a likelihood. Okay? This is a probability of observing a certain number of data, certain number of truths, for example, a certain number of diseased trees, given a true value of theta. If theta is 0, that is that there is no disease in the forest, then you observe 10 diseased trees out of 20. That value of theta, that probability is 0. Because you cannot see any X being diseased if theta is 0, by definition, right? And so this thing forms a likelihood. It forms the probability distribution of seeing the true number of observations of data given a set of different values of the possible model, theta. In our forestry example, there's 2 possible outcomes for every data, for every single observation. And so, because the trees are either diseased or not diseased. And so the model that we're interested in is the binomial function, right? And this is saying that the likelihood distribution of data given a particular value of the model follows the binomial function with some value theta, and our n is determined by how many trees are in the sample. One of the ways that we can estimate the value of theta is by doing what's called a maximum likelihood analysis, maximizing the likelihood, maximizing this probability of X with respect to theta. Now, we'll look at this maximum likelihood stuff more in the inference part of the course in the last section. But for now, all you need to understand is that what we're doing is we're finding the value of this probability that is the maximum for a particular value of theta. Okay, so like I said, if we had, for example, the case that the true underlying case that every single tree in the forest was healthy, okay, that this value, theta, is 0. And then we observe X is equal to 0. then the probability of that value of observing zero disease trees, given that there is an underlying truth of zero disease, will be quite high. Similarly, though, it's difficult to tell the difference between observing no disease trees and theta being very, very small. Non-zero, but very small. And so this probability distribution will tail off from zero, where it will have its maximum, to higher values, where it becomes less and less likely that you didn't see a disease tree given a true value, a true fractional disease of 10%, 20%, 30%, 80%. So that's the process of maximum likelihood. It's the process of defining a maximum likelihood estimate of theta. The crucial part is that in this maximum likelihood analysis, in this analysis of the likelihood here, theta is treated as a constant at every instance of the realization of the model. Okay, so it is pick a value of theta, calculate the probability, and then move to a different value of theta. Calculate the probability, etc., etc. The fact that theta is treated as a constant is the absolute cornerstone of classical statistical theory. Okay, and this is probably a spoiler because that'll give you an indication of where we're about to go. Bayesian statistics, the fundamental difference between Bayesian statistics and classical statistics, classical inference, is that in Bayesian statistics, the model parameter theta is defined or treated as a totally random quantity. And what that means is that we can analyze the data set and the model using simple probability theory alone, without any other changes, without any other modifications. And so Bayesian inference is based almost entirely in the concept of this thing called the posterior probability distribution. Okay, the posterior probability distribution, and be careful you don't get this mixed up by what we were just looking at on the last slide, is the probability of theta given x. It's the probability of observing the model theta given the data x. It's the opposite conditionality of what we saw in the likelihood. And the way in which we obtain the value of the posterior probability distribution, or rather the distribution of the posterior probability distribution, is via Bayes' rule, which is where Bayesian inference gets its name. Is by this guy Bayes, who created this rule, which has been used to create the posterior probability. The Bayes rule, or Bayes theorem, is defined, and we've already seen it, is defined as the posterior probability, P of theta given x, is equal to the likelihood, P of x given theta, times P of theta divided by P of x. Okay, where the denominator in this equation, P of x, is the integral over all possible model values and given the data. This thing here is a function, as it says here, is a function of only x. Okay, so for a single static realization of the data, this denominator here is a constant. Okay, and that means that you can calculate what's called the unnormalized posterior probability density as just the proportionality between the posterior probability, P of theta, and the likelihood, P of x given theta. As I said before, the value of this thing, this P of x given theta, this is the classical likelihood that we saw last slide. Okay, and so what we're doing here is we're just taking the classical likelihood and we're inverting the conditionality. from instead of being the data conditioned on the model to be the model conditioned on the data. Most importantly, this P of theta. The P of theta is what we refer to as the prior probability distribution, or just the prior for short. The prior represents all the previous belief that we have about the possible values of theta prior to observing any data, to observing any information. The prior is the most important part of what we're about to look at. So we'll go through it quite at length. When we're trying to make an estimate of some parameter theta, we almost always have some prior knowledge, some prior belief about the values that theta can take. If we take, for example, some data model, let's create a random set of data, and let's give that data model a binomial distribution with 10 trials and some probability, theta. And let's say, that every observation of those 10 trials was a success. X equals 10. Given these observations, given this data and this model, in classical inference, we would reject any hypothesis that theta is less than 50% in favor of a different hypothesis, that should be a 1, that theta is greater than 50%, with absolute certainty, essentially. The reason that we would make that rejection, or rather we would make that change of hypothesis, is because in classical theory, the maximum likelihood of this data, this binomial data, given the possible values of theta, is maximized at theta is equal to 1, because every trial was a success. Okay, so the maximum likelihood of X given theta is at theta of 1. Now, that might not seem like a problem to you, right? We've just said that the data tell us that we have 10 successes. It's a binomial distribution with unknown probability. So it's a coin with unknown biasing, and we flip that coin 10 times and we see 10 heads. And that might lead us to believe, rightly, that the most likely bias on this coin is that it always throws a head. And that might be totally fine. But the problem, or rather the nuance, comes when we start to realize that this is exactly the same model that we have from our 3 scenarios at the beginning of the lecture. We have a binomial choice. Does he predict the 10 correct outcomes or not? Does the wine taster correctly identify the right wine 10 times in a row? And does the musician identify the correct composer 10 times in a row? All of them succeed. X equals 10. And therefore, in classical likelihood, the probability of them telling the truth is equal every single time. So we considered these 3 scenarios. We considered our drunken coin toss, our soothsayer, who said that he can correctly predict the 10 outcomes of the coin by seeing the future, and he correctly predicts the 10 outcomes of the coin. We had our wine critic, who said that they could identify the wine from France, and they correctly identified the wine from France and Spain 10 times in a row. And there was our pianist, who correctly identified the 10 composers in a row. All of these in classical inference have the same probability. We would be forced to reach the same conclusion for all three scenarios, and that is that the most likely value of theta is 1. The most likely value is that they are telling the truth. However, as I'm sure is true for you, as it was as true for me, our prior beliefs are probably in conflict with this. Our prior beliefs tell us that there is a fundamental difference between these three scenarios, and a fundamental difference that is not reflected in the likelihood. It is not reflected by just the classical statistics. So the way in which we're going to go through this is I'm going to show you now what my graphs look like. And we're going to use those as an example. But you should think about this in terms of what your graphs look like and see how you interpreted things and how the observation of the data modified your interpretation. So for my starting graphs, I produced the distributions that I'm about to show you. But you'll probably get a pretty good indication of my sort of all or nothing feeling about this particular scenario. First things first, I fundamentally do not believe people can see the future. It's not going to happen. And therefore, my prior belief for scenario 1 is almost exactly 0 probability at every value that is not 0, right? So a peak at 0 probability and essentially no probability mass anywhere else. For the wine drinker, I think it's probably unlikely that our friend spent lockdown learning how to be a sommelier. But I'm not completely closed off to the probability that he might have. And so I've given him a very, very slight uptick in probability mass at 0 probability, but a non-zero probability at 1. So I'm giving him a chance. I'm saying that, look, it might happen, but I'm not thinking that it's the likeliest outcome. And finally, for the pianist, I think that somebody deciding to get back into learning the piano like they did when they were a child is something that sounds totally reasonable for someone who is in lockdown, especially if they've learned it originally as a child. And so I think that there's a very, very good chance that this person is telling the truth and that there is, very little probability that they are lying. So this is my 3 prior beliefs. These are my 3 priors. What then happens to my 3 prior beliefs? Well, actually, I want you now to pause the video again and just have a look back on your priors, reflect on what you've drawn and how you can interpret them, how they compare with mine. It's like I said, this is a totally subjective thing. It doesn't matter if yours are the complete opposites of mine. Perhaps you, totally fairly, are much less of a skeptic about people being able to see the future than I am. Totally fine, right? And so your probability for distribution for this one might extend, say, 50% at 0 and 1. Where you're saying he could or he couldn't. I don't know. I want to see the data first. There are no wrong answers. And I'm not meaning that in terms of, I want to make you feel good about yourselves. What I mean is that when it comes to specifying a prior, by definition, there is no wrong answer. The prior that you specify is your prior. It is entirely subjective. And what that means, we're going to see, is that the outcome of Bayesian inference will be vastly different depending on your prior belief. It's a fundamental part of Bayesian statistics we're going to see. These graphs that you've drawn are your priors. Now we're going to look at what happens after we see the data. So your second set of graphs, after you saw the data, these relate to how you feel about the outcomes, right? It's very likely that if you, like me, had very, very low probability of success for one or more of these scenarios, when you saw the data, your initial reaction was probably, I still don't believe it. Fine. I good on them. They guessed it 10 times in a row. It's very unlikely, but good on them. They did it. I still don't believe it. And if your graph after the fact, after seeing the data, is still very, very low probability at one end, at the negative end, at the lying end, like it is for me, for example, with our soothsaying fortune teller, then that's an indication that observing the data has had very little influence over your prior. However, let's put that one aside for a second and let's look at my other two outcomes. So after observing the scenarios, my feeling about how likely it is that these people were telling the truth has changed somewhat for these two distributions. So for scenario 2, our wine drinker, I now have totally flipped my opinion. Initially, you'll remember my opinion was that this person is probably lying. It's more likely than not that they didn't actually spend the lockdown learning how to become a sommelier and that they don't know what they're talking about and that this is going to end very badly for them. But having observed the data and given that my probability density had some finite probability of them telling the truth, I've then said, no, I was wrong. My new probability of them telling the truth is inverted. Now I think that it's actually quite likely that they did spend all this time studying and learning how to become a sommelier. Similarly, for the pianist, I started with already a very strong belief that this person was going to be telling the truth because I believed it from the beginning. And the observation of those 10 data that they got correct has only hardened my opinion, has made me much more confident that this person is telling the truth. And so you can see that just in summary, my fortune teller opinion was unchanged. I've changed my opinion about the wine drinker, and that I think I'm even more confident about the classical pianist having actually done this. Now, what you had on your x-axis was the fractional chance that they're telling the truth, and that's really not that much different from the fractional chance that they will succeed if we do another set of 10 trials, right? This distribution that you have just calculated is something akin to the posterior probability. It is the probability of the model, whether they're telling the truth, 1, or lying, 0, given the observations of the data, P of theta given X, the posterior probability distribution. The important part, or the most important part of understanding or interpreting the distributions that we just had, or what you have on your page, which are your posterior probability distributions, is that every single person who watches this video will have a different posterior, essentially. Every single one of you will have specified slightly different priors, independently from one another. And those priors influence the posterior probability. Now, you all saw the exact same data, but you will all infer different values of theta because your prior belief was different. And that is a fundamental tenet, a fundamental property of Bayesian inference. Essentially, it boils down to this. Experiments are not abstract devices. They are not something that happens in the universe devoid of all other interaction and all other knowledge. These are things, these are processes, these are occurrences that we investigate with some underlying knowledge or understanding of the process that we are interested in, of the process that we are experimenting. And that underlying knowledge influences the way in which we interpret the data. In the classical inference form, there is no method for creating any sort of subjective outcome. The data given the model is an objective quantity. It doesn't matter what you think, that's the probability of the data given the model. But the probability of the model given the data is a subjective quantity because it is influenced by the prior. And so Bayesian statistics creates some mechanism for drawing inference from the combined information of knowledge, prior knowledge, and observed data. There's four fundamental aspects that characterize Bayesian statistical inference. The first is the prior, we've already spoken about. All problems are unique to having their own context. And that context derives prior information. It gives us prior information, and it's the formulation and the exploitation of the prior that sets Bayesian statistics and classical statistics apart. Okay? The second fundamental thing about Bayesian statistics is what we were just saying about subjectivity. Bayesian statistics formally creates an explicit notion of how probabilities are subjective. They are not God-sent objective things. They are subjective based on both the data and the knowledge that we bring into an experiment. The third thing is the idea of self-consistency, which is that by treating theta as a random variable, we can then generate the entire basis of probability of Bayesian statistics, Bayesian inference, from probability theory alone. And this is why we studied probability theory before doing Bayesian inference, because all of the action that we are going to do in Bayesian inference is based in probability theory. We can formulate all of our beliefs, all of our data, and all of our inference about any model and any data given probability distributions. And we can then use those to create the posterior and then directly derive information from the posterior. The last thing is what I've listed here as no ad hocery. Ad hoc being a Latin term. What that means is that Bayesian statistics, with the formulation of the prior and the posterior, sort of sidesteps the tendency that we have in classical inference to pick the method of estimating the parameter that we like the best, or that we think is the best given what we want to get out. Okay. It's very easy to pick a particular way of summarizing a maximum likelihood that suits our needs. But that is a totally ad hoc choice. It is something that we decide without any justification, deciding to use just a point estimate or to use just a 95% confidence interval. These things don't have any justification behind them. They are a choice that we make, and we make ourselves and for no apparent reason other than we want to do that. And that is the ad hocery. Conversely, when the posterior probability distribution is a probability distribution, there are simple and finite ways that you can interpret that distribution. You have the full PDF, and that full PDF encodes all the information that is required for statistical inference. You can summarize that PDF, sure, but you don't have to. The PDF encodes all of the information and the entire inference about theta. Okay. We're going to go through now and talk about Bayes' theorem. Bayes' theorem, we've already looked at a little bit, so I'm going to go through this, reasonably quickly. What we looked at with Bayes' theorem was how it basically came out of conditional probability. So when we started talking about conditional probabilities, we looked at the intersection, we looked at conditional probability, and what fell out of that conversation was that if you have two probabilities, two events rather, A and B, and there is a finite probability of A occurring, a non-zero probability of A occurring, then you can construct the conditional probability of B given A as the conditional probability of A given B times the probability of B divided by the probability of A. This is what we have seen already a couple of slides ago. Bayes' theorem, as we've said, is the application of reversing the conditionality, okay, to show how B given A is related to A given B. Now, there's a really useful, for educational purposes, less useful when we're actually doing this in the natural sciences, but for educational purposes, there's a really useful extension of Bayes' theorem, which takes us to a very specific, particular case of experiment where you have K possible outcomes, C1, C2, C3, all the way through to CK, and that these outcomes partition the sample space. That means that the intersection of any two outcomes is 0, so they do not overlap in the sample space at all, but that the union of all of these different outcomes, so the sum of all of the parts of the sample space is of all the different events outcomes is the sample space. So the union of C1, C2, all the way through to CK is the sample space. And when you have that particular setup, when the outcomes are unique, they don't overlap, and they fully represent the sample space, then you can reformulate the Bayes theorem as the probability of Ci given A is the probability of A given Ci, the likelihood, times the probability of Ci, divided by the summation from j equals 0 to k of the probability of A given Cj and the probability of Cj. This thing here is the probability of observing the data given all of the finite outcomes, C1, C2, C3, all the way through to CK. Okay? So it's taking the fact that these are finite things and using that to our advantage to create a finite, simpler expression that we can use to explore Bayes' theorem. And if you haven't realized the sort of thing that this experiment is describing, then get ready because we're going back to the urn. So you'll remember that we spoke about the urn theory of probability back when we spoke about probabilities, and we're now returning to the urn. So the urn model without replacement is one of these cases where the outcomes are distinct and they fully tessellate the sample space. So let's take an urn that we know contains 6 balls. And those balls are of unknown color. Okay? We then draw 3 of these balls at random without replacement, as I said, and every single one of those 3 turns out to be black. What is the probability that there is no black ball left in the urn? Now that might seem like an impossible thing to calculate at the top of just at face value. But it turns out that it's very easy to calculate given Bayes' theory, given Bayes' theorem. So we can let A be the event that 3 black balls are drawn from the urn, and Ci being the event that there are actually I black balls within the urn. Right? So there is a finite number of balls in the urn, 6. And so the number of possible outcomes is C of 0 through to C of 6. C of 0 being the circumstance that there is no black ball in the urn. C of 6 being the outcome that there are 6 black balls in the urn. And we can calculate using Bayes' theorem the probability of C3 given A, the probability that we have observed the probability that there is truly only 3 black balls in the urn, given that we have already observed 3 black balls. And that probability is just, that conditional probability is just this from Bayes' theorem. Now, this probability, this likelihood, the probability of seeing 3 black balls, given that there are actually only 3 in the urn, is simple to calculate. That's just 3 over 6, because the probability of drawing a black ball first is 3 out of 6. And then you've drawn 1, so the next draw is 2 out of 5, and the next draw is 1 out of 4. Right? So it's easy to calculate this probability. The critical issue is what value do we assign to the probability PC0, PC1, PC2, all the way through to PC6. These are the prior beliefs. So before we observed anything, what prior belief do we assign to the probability that there exists I black balls in the urn? Yeah. Now, without any additional information, you might just quite logically assume there's no way to know, right? It is equally likely that there could be 0 or 1 or 2 or 3 or 4 or 5 or 6, right? And therefore, you would assign the prior probability P of Ci is equal to 1 over K, where K is the number of possible outcomes, which is 7. 0, 1, 2, 3, 4, 5, 6. So we can use this prior, sub the prior back into our Bayes theorem, and we get the probability that there is truly only 3 black balls in the urn, given that we've observed 3 in our first 3 draws, is equal to the probability of observing 3, given that there is 3 in the urn, times the prior probability of there being 3 in the urn, divided by the summation of all possible ways of seeing our data, all possible combinations of seeing 3 draws of a black ball, 3 black balls first, at 1, 2, and 3, given that there are 0 in the urn, 1 in the urn, 2 in the urn, 3 in the urn, 4 in the urn, 5 in the urn, 6 in the urn, right? Now, obviously, the probability of observing 3 black balls, given that there is 0 in the urn, is 0. 3 black balls, given that there is 1 in the urn, is 0. Probability of observing 3 black balls, given that there is 2 in the urn, 0. So the first three terms in this summation are all zero because this probability of observing the data given the model has to be zero. I've pulled out the prior out to the front here of the summation, which is why it's wrapped in brackets. And then this here, these four terms, 1, 2, 3, 4, are the probabilities of observing 3 black balls, given that there are 3 in the urn, 4 in the urn, 5 in the urn, and 6 in the urn. And when you calculate this summation, what you find is that this posterior probability is equal to 1 on 35. So what that means is that the observation of the data has updated our prior belief from 1 in 7, there is a 1 in 7 chance that there is truly 3 black balls in the urn, to being that there is a conditional probability of there being 3 black balls in the urn, given that we've observed 3 draws from the urn already, and they're all black, is 1 in 35. It is much, much less likely that there is only 3 black balls in the urn after we observe those first 3 data. Okay? Our posterior probability of the truth, being that there is only 3, has decreased significantly because we have made this observation. Okay? That we were just talking about is when we formulate Bayes' theorem in terms of finite probabilities. If now we instead formulate Bayes' theorem in terms of random variables instead of individual probabilities, then our random variables, as we've discussed before, are usually given the probability distribution symbol lowercase p. Bayes' theorem then changes a little bit, not significantly, and it now says that the continuous probability distribution of the value of theta conditioned on x, so the value of the model conditioned on the data, is equal to the likelihood, the value of the data conditioned on the model, times the prior distribution, these are now continuous probability distributions, divided by the integral of the data given all of the different observations that we have. The probability of the prior, all of the different priors that we have, the whole distribution of P of theta, times the conditional probability x given theta, integrated over theta. Okay, so what we're doing is we're integrating out all of the possible values of theta. This is a continuous function, so it goes from being a summation to an integral. And we now have, again, P of x on the denominator, independent of theta, can be considered a constant as it did previously for fixed data. And therefore, that even when we have a continuous distribution of x and a continuous distribution, probability distribution of theta, nothing really changes. Okay, we now have this integral on the bottom, but other than that, nothing really changes. P here now represents the probability density function of x if it's a continuous variable, but if x is discrete, then naturally it's the probability mass function. Remember, we discussed the difference between these two things is just whether you have discrete data or continuous data. As with x, theta now can be discrete or continuous. It's a probability distribution now. And so the denominator, once again, if it's a discrete thing, goes back to being a summation. But if it's a continuous thing, it's an integral, like we just said. And again, because it marginalizes over the value of theta, it's only a function of x. So we can still do this proportionality game. Even in the case where theta is a random variable and when x is a random variable, we can still play this game of ignoring the constant denominator and using the proportionality here to come up with the fact that posterior probability is proportional to the prior probability times the likelihood. times P of the data given them. Okay. So nothing really, that's just saying that nothing really changes. When we actually want to do Bayesian inference, there are 4 steps, which we've already done a few times already, but I'm writing down to be explicit. There are 4 steps to Bayesian inference. The first is you have to specify a likelihood model, just like you do in classical inference. Okay, there has to be some means of calculating the likelihood of observing the data given the model, P of X given theta. Step 2 is specifying the prior. You need to define the prior belief that you have over the value of theta, or the distribution of possible values of theta, before observing any data. Step 3 is calculate the posterior probability distribution using Bayes' theorem. And step 4 is use the posterior probability distribution to draw your inference. Calculate the maximum value, the mode of the posterior, the mean of the posterior, the confidence, the highest probability density in the posterior, and use those for your inference, or use the posterior as a distribution itself for your inference. These are the 4 steps that are part of Bayesian statistics. How we actually do this in practice can be computationally difficult. And the main reason it can be difficult is because of the normalization integral on the denominator. That integral can become very, very difficult to calculate with surprisingly simple distributions of data and priors. We'll see that more next week. But for some choices of prior and likelihoods, the integral can be either avoided entirely, or you can use special techniques that we'll go through in order to solve the calculation. But let's go back to our 3 scenarios one last time. And let's specifically go back to my prior distribution. So I showed you my prior distributions. They were these ones here. What I didn't show you, or what I didn't specify, is that the actual functional form of these priors is all beta functions, what we spoke about in our probability distributions discussion. So the probability, so our value or rather my prior on theta is that it is a beta distribution with some characteristic shape parameters alpha and beta. And therefore, because it's a beta distribution, it has the probability function of this, which is what we saw in our lecture on probability distributions. This front thing being essentially a normalization, and the main brunt of the beta distribution being this thing here. The theta to the power of alpha minus 1 times 1 minus theta to the power of beta minus 1. For my 3 different priors, I specified them to be these beta distributions here. Alpha is equal to 0.1, beta is equal to 100. That's the very steep red curve that you've got over here at 0, piling up at 0 probability. For scenario 2, I specified beta alpha is equal to 0.7, beta is equal to 1, and that gives me this fairly flat distribution you can see here. And for the third scenario, I said alpha is equal to 10 and beta is equal to 0.5, and that gives me this blue curve here. Now, the reason I'm telling you this is because what we can do is we can actually go through and we can calculate the posterior probability using just the mathematics analytically. So let's do it. The likelihood function we know is a binomial, right? Because there's 2 possible outcomes. And the data that we know we've observed, so this is the binomial distribution function. This is the probability of observing X observations given theta, is our n choose X times theta to the power of X, 1 minus theta to the power of n minus X. So this is the binomial distribution. And we know that we observed n equals 10. So let's actually calculate it. Let's just go through the math and calculate the probability distribution, the posterior probability. So our likelihood looks like this, okay? Because we have n equals 10. My priors are all of this format, which let's just say are proportional to this thing. Let's ignore this proportionality thing at the front here, and let's just look at the important bit, the theta to the power of alpha minus 1, 1 minus theta to the power of beta minus 1. By Bayes' theorem, we have this proportionality. The P of theta given x is proportional to P of x given theta times P of theta. P of x given theta is my binomial, which I'm going to use proportionality to get rid of the 4 leading n and choose x here and just take the important bit, which is this bit here. And I'm going to times that by my prior, which is this thing here. And then I'm going to just do my combination of my various thetas and 1 minus thetas to get this posterior distribution here. The posterior of x, the probability of theta given x is equal to the, is proportional to the, to theta to the power of x plus alpha minus 1 times 1 minus theta to the power of n minus x plus beta minus 1. Now this here should look familiar because we just looked at it here. This thing is proportional to a beta function where alpha is equal to x plus alpha and beta is equal to n minus x plus beta. So by using this beta function prior and the binomial likelihood, I've ended up with a posterior that is a beta function. And therefore, I can analytically define. Okay, so this thing here is just a beta function, and it's a beta function of x plus alpha, n plus beta minus x. And because we know that this thing has to be a probability distribution, we know that it has to integrate to 1. And we know that the beta function is a probability distribution that has to integrate to 1. So it turns out that the leading proportionality constants that we had actually drop out, and they, all of the difference complexities that we had here and we had in n choose x, they all end up dropping out and being able to be just equal to this proportionality constant here for the values of alpha and beta that I've modified. That is to say, the posterior samples that I get are a beta function, and they are explicitly a probability distribution with the shape of a beta function given these parameters. So the effect of observing the data has been to update the beta distribution to have the parameters alpha is equal to x plus alpha and beta is equal to n plus beta minus alpha. Yeah? And that means I know what all these values are. I can just plot the posterior analytically, and I can look at it and I can say, how does it look? And so I'm going to do that. I'm going to take these different values and I'm going to sub them in given my priors and my likelihood and my observations, x equals 10, n equals 10, alpha and beta come from each of my different priors. And what I end up with are these posterior probability distributions. So the posterior probability of theta given the data in a purely Bayesian sense, the actual posterior probability for my priors looks like this. Scenario 1 has a peak at around 1%, around 10%, but is still fairly narrow. Scenario 2 has a strong peak at 1 and tails off moderately. And scenario 3 has a strong peak at 1 and tails off quite rapidly. Now, what the really neat thing that you can do as well, and what I can do, is that you can take your probability distributions, your priors. You can play with the beta function until you get something that is roughly what you had for your prior. The beta function is extremely flexible. Picking the values of alpha and beta will get you the values that you want, will get you a prior that you want. It's very, very difficult to come up with a prior in this sort of a scenario that you can't describe by a beta function. And you can then do what I'm about to do, which is directly compare the posteriors that you get from the Bayesian theory to the posteriors that you created in your brain by saying, how has my distribution of my expectation of theta been influenced by the data? And this is that thing I was saying about how you might learn something fun about your own brain. So these are the true distributions of the posterior that I get from Bayesian theory. And these are my posteriors that I came up with entirely in my own head. And so the first thing that should be quite clear is that my posterior for scenario 1 is quite wrong. And what that means is one of two things. Either I should have been more swayed by the fact that he saw those, but that this fortune teller correctly predicted 10 heads in a row. I should have seen that and said, wow, that's really impressive. Maybe he's telling the truth, and shifted my guess. Or more likely, I would argue, the prior that I specified wasn't a fair reflection of just how unlikely I think it is that he can actually see the future. While I said I specified a prior that was quite strict, in my mind, my true prior belief was much, much stronger. And therefore, my posterior has basically been unaffected by the data that we observed. So my prior needs to be much stronger than what I initially gave. Looking at the other two, though, they're actually not too bad. The green is a pretty good representation here of the green that I had, probably a little bit too harsh, in fact. I should have more confidence in my friend's abilities after seeing this effect, given my prior. And for the classical pianist, it's very, very good. It's very close. If anything, I'm a little bit overconfident, and I probably should be a little bit more skeptical. But you can now do the same game. You can take these things and you can go through and you can look at how your posteriors are compared to the true posteriors that you should have had, given Bayes' theory. And you can make some interesting conclusions about how your own priors and what you're actually thinking. The most important lesson that you need to take away from this is that every single one of these experiments had exactly the same data. They had 10 trials of a binomial with 50% chance, and every single one of them had an outcome of 10 correct answers. The differences that we will all have in our posteriors come from our differences in our priors. Okay? With exactly the same data, we have drawn 3 totally different conclusions. With exactly the same data, we have drawn 3 totally different conclusions about whether or not these people are telling the truth or not. And that difference, the difference between the blue and the red and the dashed green, is entirely driven by prior belief. And that is the fundamental tenet of Bayesian statistics. Yours will all be different, as mine are. And this should basically show you how significant, how important a role prior belief plays in statistical inference, in Bayesian inference. So we're going to end today with 3 really important lessons that I think you should all know, and you should all have learned, hopefully, from this lecture. So please feel free to go back over this video, watch the different parts of it, have a play with the different beta functions. I've intentionally left the R code, and it is R code, all of the R code for how I've constructed my plots and my beta functions and things there. So you can look at these directly and you can calculate your own posteriors and calculate your own priors and plot them and play with them. If you would like, as I said in the previous lecture, you can do all of this in Python as well, using the NumPy functions that they have for the beta distribution and stuff like that. You'll be able to figure out how that works. And if you can't, it's very easy to Google the NumPy functions. Please, over the course of the first half of this week, or the next 5 days, put your questions on the Slido, anything that you have that might be confusing or you might not have understood. And on Wednesday at our normal time, we will meet and we will discuss the questions that you have about this lecture. Thanks very much for paying attention and for watching this lecture. If you have any thoughts about whether or not this was a good format, if you would like to have it in this sort of a format more often in the future, then please let me know, and we will think about whether or not that's something that we can do. Otherwise, thanks very much, everyone. I look forward to seeing you all on Wednesday for our discussion session. And until then, have a good week.